Hello everyone. So in this video we're going to talk about chapter 11, which is association between categorical variables. We'll get started. For the outline of what we'll talk about today, first we'll talk about some notions that we have gone over before in earlier chapters with respect to categorical variables and other and statistics sort of in general, which are independence, and then of course the opposite, which is dependence. So we'll talk about independence and dependence, and then we'll talk about uh, what this chapter is really about, which is testing categorical variables for independence. And that is called, the test that we're going to do is called Pearson's chi-square test for independence. There are many variations that do different things other than independence, but frankly, we just don't have time uh, to do that. Okay, or even if we did have time, it's in a remote learning environment, and I just don't feel like it. So this will be an abridged chapter 11 from what I usually do, but hopefully that doesn't disappoint you too much. So we'll get started. So we've been talking about in all the chapters that we've been doing p hat and x bar, but what they have in common is that the variables that we've been talking about are quantitative. So what do we do, or what do we do for categorical variables? So can we do the same thing? Do we have to change what we do? How different is that going to look? All these questions we're going to try to answer here. And so the first answer, which is simple, is yes, we can do inference for categorical variables. It just looks very different than what we're going to be used to. But the ideas stay the same. Of a hypothesis test, it's just going to look very different. So before we get into the actual hypothesis test, we've got to revisit some important ideas from the earlier chapters, i.e., association and independence. Association is the same thing as dependence. So, association is some type of dependence between two variables. Great. Okay. Independence is a lack of association. So we've got these two which are opposites of each other. Okay. Independence is nice in statistics for a number of reasons that we won't get into in this course. So an example of association with categorical variables is here. This is a simple contingency table of income and then happiness from the 2008 General Social Survey. So as a reminder, a contingency table is a table of numbers that have been what are called cross-tabulated. We have cross-tabulated for two categorical variables. And so the data originally looked like they asked a bunch of people their income, okay, and not actual income, but whether their income was above average, average, or below average, and also their happiness level of not too happy, pretty happy, and very happy. And so there are a lot of people who answered those questions. I want to view both of them together, not as a long bunch of responses, but as to see who answered the same in both categories a number of times. That's a contingency table. Okay, so hopefully that's pretty clear. I'm sure my explanation there didn't make it any clearer, but oh well. So association, or lack of it, is probably pretty hard to just look at the table and see. If you look long enough, you can get some ideas. So you'll see that it's very uncommon to have above average income and be not too happy. Okay, it looks like there are a lot more people who have average and below average income and are not too happy when compared to above average income. So there does look like there is some trend there, and then you can look across the different columns and rows to see if there's something else there. But it's kind of hard to look at counts. And so what we might want to look at is percentages. So I can compare I can compare the percentages. Percentages are easier because it's all on the scale of 0 to 100, and so it's easier to see differences there. So if you look here and you compare the 3 different happinesses for each level of income, you'll see a pattern. It might be a small one, but I think you can see a pattern that, especially for below average people, there are a much smaller percentage that are very happy as compared to above average and average. And then similarly on the other end, there are a much smaller number of people who are not happy and have above average income when you compare to the same things for average and below average. So that might be a way to sort of look at association, but of course that's in just in your thoughts. We need to formulate that statistically or probabilistically or mathematically, however you want to think about it. Each row of the table represents conditional probabilities, and so how did I calculate these probabilities? I took the counts inside the table and divided it by the row totals, not the column totals, but the row totals. And so these represent conditional probabilities. Their happiness conditioned on the level of income. And so we've talked about conditional probabilities and marginal probabilities before. These are the same things. Each row forms what's called a conditional distribution for happiness given a particular level of income. If the variables were independent, then the conditional distributions across all levels of income, for this case, would be the same. Okay, and so we see that they're not. If they were the same, the percentage of people who said not too happy for each income level would be the same. The percentage of people who said pretty happy across all income levels would be the same, and so on and so forth. We can also look at this in a side-by-side bar chart. It's just the probabilities there in that table, but as bars on a bar chart. Okay, but it's easy to see in this graphic that the heights of the bars are not the same across all 3 happiness levels. Okay, and so if it were independent, then for each section of 3 bars, the heights would be the same. It wouldn't be the same across all of them. It just needs to be the same across the 3 that are together. Okay, so that's association in sort of a holistic way, if that's the right word. We've also discussed it more formally in a probabilistic way. So we've also discussed independence more probabilistically. And what we said is for any 2 events, whatever the events are, A and B are independent if and only if the probability of them happening together is equal to the probability that one happens times the probability that another happens. So that's what we're going to call independence. Okay, and with that, we can talk about conditional probabilities and other ways to satisfy independence. And that is the probability of A given B is equal to the probability of B, and the probability of B given A is equal to the probability of A. So you have to search back in what we did when we were in face-to-face mode with these kind of probability statements. I mentioned the second 2 because that's what we were really talking about in the last 2 slides. Were those conditional probabilities or the conditional distributions were the same across all three levels of the other variable. Now, it turns out that it's very unlikely for a table to exhibit exact independence. Okay, so it's very hard for a table in the wild, when you actually like go out and get a sample and come back, it's very hard to satisfy that independence uh, assumption in the way that I talk about in the last few lines of this slide here. Like the probability of A and B is equal to the multiplication of the marginals there. It's very hard to do, okay, and it comes along with the same idea as there's no probability at a point for continuous variables. There are just a bunch of tables that could happen. It's very unlikely that you happen upon one of them that actually exhibits independence. And so what we have to do is we have to sort of soften our idea of independence or no independence and use a hypothesis test to test if it's plausible that this table that I got out in the wild really came from a population where the two variables are independent. Okay, and so this is the same thing that we've been trying to do the entire time in all our inference chapters, but it's just with a new setting. So I have a picture here that hopefully will help you try to understand what's going on. Okay, if it confuses you, that's okay. This is never going to show up again. This is actually from my research that I do as a statistician. Okay, so I have what looks like a pyramid with some stuff inside it. That pyramid is called a simplex. And this specific simplex is called the probability simplex. And inside it are a bunch of points. Each point represents a possible contingency table. Okay? And specifically here I'm in 3 dimensions. So it represents a 2 by 2 contingency table. And so all possible 2 by 2 contingency tables are different points inside this simplex thing, whatever that is. Okay, so it looks like a pyramid. It's not a pyramid. It's called a simplex. Okay, and so I observe that black point in there. Okay, so that's the table I observe. And then you'll see this red surface that sort of snakes throughout the simplex. That red surface represents all tables that actually exhibit that independence that I was talking about before. Okay, so there are a bunch of them, but it's actually really unlikely that I see any of them when I actually pick a table out from my population. And so the question is, in this hypothesis test, how far away from that surface is the point? That's the sort of decision I'm going to make. If the point is really far away from that surface, then it's probably unlikely that the table came from a population where the variables were actually independent. But if the table is pretty close to that surface, then it might be actually plausible that the table did come from a population where the variables were independent. Because of course we know that when you take the sample, it may not be representative of the population. There's some variance involved there. And so we have to understand that variance. Okay, so keep in mind this picture when you're trying to think about the problem geometrically. Okay, and so the question is, what is the distance from the point to the surface? And so that's actually a very challenging question because I don't quite know how distance works in this setting. Okay, so do I make a straight line from the point to the surface? And an even tougher question is, where on the surface do I make the line from the point to the surface? Okay, I can make a line from the point to any point on the surface, but which one makes the most sense? That's what the people who actually came up with this had to think about and deal with We don't have to think about it, but it's there for you to sort of ponder if you're really bored. So now let's go on to the hypothesis test. So these are the null and alternative hypotheses we are testing. The null hypothesis is that the two variables are independent. Okay? And then the alternative hypothesis is that the variables are dependent. This is exactly, you can take away the associated. This is exactly how I want you to write the hypotheses. There are no symbols involved. There's no nothing, just these. Okay, so this is exactly how I want you to write it with the associated taken away. All right. And so the questions that I have to come up with are the questions that I pondered in the last slide. How do I calculate the distance from the point to the curve? Which point on the curve do I actually choose to compare to that point? And then what assumptions are involved in this process? Okay, so let's tackle that first question. How do I calculate the distance from the point to the curve? Well, I don't have to ponder it because, of course, Pearson pondered this. Okay, and of course, Carl Pearson came up with a method to calculate the distance from the point to the curve in a sort of statistical distance way, and not in the usual distance that you would talk about in a mathematics course. Okay, so he came up with this quote-unquote distance right around the turn of the 20th century. And so I'm not sure if they actually talked about this in the Lady Tasting Tea yet, but they certainly do sometime in there. And so the distance that he actually came up with, which is called Pearson's chi-square distance, and we'll talk about why it's called chi-square in a second, is this. It's sort of weird, so I call it T, is the sum of this O sub I minus E sub I squared divided by E sub I. The O sub I is the observed cell count for the ith cell of the table. So if I look at my table and I pick a particular cell and I look at the count in that cell, that's O sub I. Okay? And then E sub I is the trickier one. It's the expected cell count for the ith cell of the table if the table was independent. Okay? So it's that sort of like null hypothesized value if in reality the variables were independent. We don't know how to calculate those yet, okay, but we will soon. So I have O minus E squared divided by E. I calculate that for every cell in the table, and then I add them all up, and I get T. So that T is going to be my test statistic in the end when we actually get to a hypothesis test, okay? But that's the distance that we're going to use. So like all sample statistics, T has an associated distribution, and the distribution that T has is called a chi-squared distribution, okay? A chi-squared distribution. This is a new distribution. We haven't learned about this yet, and so let's take just a little bit of time to talk about it. So the chi-squared distribution is a family of continuous probability distributions. So it's like the normal in that it's continuous. It takes values in an interval, okay, not actual like point values, okay, or however we defined continuous before is on an interval. Discrete is a set of points that you can count. Okay, so continuous, it's a continuous distribution, and these are its properties. So unlike the normal, or like the normal, it's always going to be unimodal, so it still has one mode like most other things that we've dealt with so far. But unlike the normal and the T distribution, the chi-square distribution is usually skewed to the right. Okay, and so the mass of the distribution is actually on the left side of the points. And it's always positive, so it always takes on positive numbers, and so I can't plug in or I can't substitute in negative values in and get something out. It's always positive. And it's characterized or parameterized like the t-distribution by degrees of freedom, whatever that's called, okay, whatever that means. And I'm going to denote degrees of freedom here as a nu, okay? And so how I denote a chi-squared distribution, or how I denote a random variable that has a chi-squared distribution, is like that, okay? So it has the chi-squared, and then in the subscript is where I put the degrees of freedom nu, okay? And then I've always put in these past slides the PDF of that distribution. You don't really need to worry about it, but there it is, just for posterity. Okay. This is what a chi-squared distribution looks like for different values of its degrees of freedom. And so you'll see that it's quite skewed when the degrees of freedom is small, and then as the degrees of freedom get larger, it becomes more and more like the normal distribution. So it becomes less skewed, more symmetric, so on and so forth. If you have an infinite number of degrees of freedom for the chi-squared, it's going to look really normal. Okay? All right. So the next question is, how do I pick a point on the curve of independence that I compare to my point? Okay? And that simplifies to asking, how do I pick the e's sub i's? Okay? And so the answer to that is quite simple. Independence, as we stated before, is that the probability of the joint is equal to the product of the marginal probabilities. And so we're going to use that exact formula in conjunction with the tables that we actually observed to get our expected counts. Okay? And so our expected cell counts are this: the row total times the column total. And so how that sort of works back to what I just put on the last two builds are that the row total is kind of like A. Okay, if A are the variables in the row and B is the variable in the column, then the row total is sort of like the probability of A if I divide it by the total sample size. Okay, and so row total times column total divided by total sample size will get me that E sub I. Okay? Now, I went through that fast and I didn't really describe it because software is always going to do these calculations. I will never make you calculate expected cell counts, okay? Because that's just so 1990s and 80s and before. Okay, so we have computers, they will do it for us, and we will be happy with it. So now let's get to the actual hypothesis test that I expect you to do. And I spelled hypothesis wrong, please forgive me. So I have the hypotheses, which I talked about before. You can take away associated, but leave the rest. The significance level is going to be the same, as always. Okay, problem specific, but it'll be something like 0.01 or 0.05. The assumptions involved in this test are threefold. Okay, the first assumption is that both variables are categorical. That's kind of like a duh assumption. That hopefully I give you situations where both are categorical. Okay, that's going to be always assumed pretty easily. The second one is that data are again taken randomly. There's some randomness involved, which is needed in pretty much anything that we do. That will be pretty much an automatic one. And then the one that you're really going to need to check is this: all expected cell counts are at least 5. Okay, so you may ask, well, why the heck do you have to have all expected cell counts at least 5? It's for theoretical reasons. The things that go on sort of under the hood or behind the scenes of these tests rely on theorems from statistics that invoke certain things, and it needs some threshold to invoke them, sort of. And so this is like with everything that we've done, we've had to have certain things greater than such values. It's basically the same reasons here as it was there. Okay? The test statistic is that. Great. In practice, I'll only require the number, not any calculation. So you'll get the test statistic out. I just want you to tell me what that test statistic is. Okay? And by the way, all of these steps are required, not optional. So you need to do all of them. Okay. The p-value is always going to come from a right-tailed test this time. So before, in all the other tests that we've done, we've had sort of three options for how the alternative hypothesis goes, and then in turn how the p-value calculation goes. Well, that's different here. It's always going to be a right-tailed test. Okay, always a right-tailed test. And so here's the calculation of the p-value, probability that t is greater than t, okay, where t has a chi-squared distribution, and the degrees of freedom for this specific hypothesis test for independence is r minus 1 times c minus 1, where r is the number of rows and c is the number of columns, okay, in our contingency table. All right, great. This is what it looks like visually. We're always going to be looking for that right-tailed area. Okay, we're never going to be looking for a left-tailed area. And so the decision and conclusion are going to be the same as before. Okay, so I'm going to stop here. I know this is a long video by itself, and I'm going to create a second, much shorter one that goes through an actual example of doing the hypothesis test with calculations in Minitab. Okay, so I'll see you next time.